All right, so now we're going to look at a couple of examples. Okay, so let's look at an example where I have a constant and a zero. Okay, so in this case, what I have is k equal to 10, and it looks like I have a zero corresponding to tau z equal to 10 to the minus 4 seconds, or omega equal to 1 over tau z of 10 to the fourth rads per second. Okay, all right. So we remember that. Okay. Now, if we do this guy in the log space, so we know 20 log 10 of h of j omega is 20 log 10 of 10 plus 20 log 10 of 1 plus omega squared tau z squared. Now, if I look at this, what I have is the additive effect of a constant and a zero. Okay, so what we talked about last time is we know that because these guys are additive, we can look at each one individually. All right, so if I'm looking, for instance, at this zero here, that says that this guy starts out at zero and then rises, we said, 20 dB per decade. Now, the notes, I derived that again a little bit more, but I mean, you can clearly see from the fact that the pole and the zero are the same. The only difference between a pole and a zero is a minus sign on a pole and there's a plus sign on a zero. All right, so clearly the effect is going to be this exact same if you make the same approximations. And this would be 1 over tau z. The only thing different here between the pole and the zero would be if you looked at the actual, if you go into MATLAB, you'd see the actual actually is about 3 dB higher at the zero frequency, whereas for a pole, it would be 3 dB lower than the approximation at the pole. All right, but it kind of makes sense why it would be higher because it's going up instead of down. All right, for a constant, right, that's just going to be a constant, right? Very easy to imagine what that's going to look like. All right, so now let's try to sketch this. Okay, so here's 20 log 10 of the magnitude of h of j omega. And then let's draw in our x-axis. So x equals log 10 of omega. Okay. Now I dimension my x-axis and I say 0, 1, 2, 3, 4, 5, 6, 7, right? Like I said, remember, for every number that I go up here on the x-axis, I'm going up a factor of 10 in frequency. So that means that, so the log of 1 is 0, the log of 10 is 1, the log of 100 is 2, 1,000 is 3, 10,000 is 4, 10 to the, sorry, that should be 10 to the 5th. The log of 10 to the 5th is 5, 10 to the 6th is 6, the log of 10 million is 7. Okay. All right, now on the y-axis, I would do something similar. So here's 20. Okay. Here's 40. Here's 60. So each of these tick marks corresponds to a factor of 10 in magnitude. Okay. So here's minus 20. Here's minus 40. Okay. All right, now what I do in this case is I look at each of these components individually. So let's start with the constant, right? 20 log of 10 is, so the log of 10 is 1. 20 times 1 is 20. So what I'm going to do is I'm going to draw the individual effect of that guy as a constant. All right, it's a dashed line going along like that. Okay. Now, this is the constant. Now, separately, right? Because these guys are additive, I can look at them separately and then add their effects. Let's look at the 0. So I know for the 0, it's going to be constant at 0 before the 0. And then I'm going to rise at 20 dB per decade for frequencies of greater than the 0. So that means, okay, so let's see. So I'm going to draw a guy here at 0 out to 10 to the 4th. And then at 10 to the 4th, I'm going to start to rise basically 20 dB every decade thereafter. Okay, so that's the effect here of the 0. Now, if I want to get the combined effect, what I do is I go along for each individual frequency. So in other words, for each value on the x-axis, and I add the effect of the constant plus the effect of the 0. All right, so out here, I have 0 plus 20. Here I have 0 plus 20. Here I have 0 plus 20, and that continues until I get to here, at which point I now begin to take off. Okay, so let's see, let's follow that guy out to 10 to the 4th. All right, so out to 10 to the 4th, those guys follow each other. Okay, now by the time I get to 10 to the 5th, the 0 is contributing 20 dB. Okay, I'm a decade above 10 to the 4th, so the 0 is now contributing 20 dB. And the constant's contributing 20 dB. So that means at 10 to the 5th, I should be at 40 dB. All right? So at 10, let's see, I should be at 10 to the 4th, I should be at, so 10 to the 5th, I should be at 40 dB. And at 10 to the 6th, I should be at 60 dB. So that means this guy's going to rise like so. All right? Now, here, so basically what I'm saying is at any given frequency, right, I'm constant and then rising. Okay? So at any given frequency, I add up the effect of the constant and the 0. So out until 10 to the 4th, I had 20 plus 0. Once I go above that, I have 20 plus whatever this guy's telling me. So here I have 20 plus 0 is still at 20. By the time I get to 10 to the 5th, the constant is equal to 20, and the 0 is equal to 20. So I have 20 plus 20 is 40. By the time I get to 10 to the 6th, this guy is at 40. The constant is still at 20, so I have 40 plus 20 is 60. All right. Really what I did was I took this whole 0 line and I shifted it up by 20. That's the other way to think of it. Okay. All right, so we've got our magnitude. Now I want to do my phase. Okay, so to do my phase, angle of h of j omega. Now I don't plot the angle on a logarithmic scale. I do plot the x-axis on a logarithmic scale. Okay, so in this case I can call this 1, 10, 100, 1,000, 10,000, 100,000, a million, 10 million. Okay? Now, the constant in this case has an angle of 0, so I can include that if I wanted to. And say, okay, the angle is 0 everywhere is along here. Okay? And, all right, what else do I have? So now I need to take into account the 0. So what I said before is the 0 causes the angle to rise. So for a 0, I get an angle that rises from 0 to 90. Okay? And it does so over the span of 2 decades. It starts taking off about a decade before the 0, and it's done, and it's at plus 90 about a decade after. So in this case, all right, I say here's 90 degrees, here's 45 degrees, And I'm going to say right here at 10 to the 4th, oops, all right, so I'm going to take off the 10 to the 4th would be here. All right, and at 10 to the 5th, I should be here. So let's see. I get something like that for the 0. So it's 0, and then it rises. And that's really the whole thing, okay? So about a factor of 10 before I start to rise, factor of 10 after, I'm done rising, and right in the middle, right at the 0, I'm at 45 degrees. Now let's look at what those look like in MATLAB. Sorry, I thought that was open. Okay, what's that look like in MATLAB? All right, here it is. Okay, so just like we said, it starts at 20 dB, and then I get to 10 to the 4th, and it starts to rise. And again, what I can see is if I look carefully right at the pole, or sorry, right at the 0, it's at 23 dB instead of 20 dB. So it's 3 dB above. And I can see, okay, here's my black line's my approximation. So about 10 to the 3rd, about a decade before the 0, I start to rise in phase. And about a decade after, I'm done. Right? And the blue is the actual. So you can see very clearly that this matches up with what we just showed. All right, now let's continue to look at some examples. Let's look at another one. All right, so here's a pole 0 diagram. All right, and I'm told that this guy's got a gain k, a multiplier, a constant of 10 to the minus 4. All right, so I got a pole 0 diagram here. So let's see what I can see for this guy. I can tell for him that h of s better be 10 to the minus 4 s, that's the 0 at the origin, over, looks like, so this is my negative 1 over tau. Okay, so I'm going to say s over 100,000 plus 1, right? So my tau is 1 over 100,000 like that. So in this case, all right, I've got a single pole, all right, and I have a single 0 at the origin, and then I have this, multiplier effect of 10 to the minus 4. So let's take that. Let's take that over here, okay? So now I'm going to say I have, for my next system, h of s is 10 to the minus 4 s over 10 to the 5th plus 1, okay? So a couple of things. I see I got a 0 at origin, which we haven't talked about those yet. I see that I have a pole at omega equal to 10 to the 5th. Okay, so let's look at how we deal with this guy. I also see I have a k equal to 10 to the minus 4. So, all right, so 20 log 10 of h of j omega is the combined effect of 20 log 10 of 10 to the minus 4 plus 20 log 10 of omega minus 20 log 10 of 1 plus omega over 10 to the 5th squared. Okay? All right. So I know how to deal with constants. I know how to deal with a simple pole like this. All right, so let's do this guy. All right. This one's a little bit tricky. All right, log 10 of omega is x. And I have 20 log 10 of h of j omega here. Okay? And I'm going to draw, here's minus 20, minus 40, minus 60, minus 80. And I'm going to draw up here 20, 40, 60, 80. Okay? And okay, on the x-axis here's this time I'm going to draw some negative values. Minus 1, minus 2, 0, 1, 2, 3, 4, 5, 6, 7. All right, so just to be clear, right, minus 2 is the log of 10 to the minus 2. This is the log of 10 to the minus 1. This is the log of 1. This is 10, 100, 1,000, 10,000, 100,000, a million, 10 million. Okay? All right, so let's go and do each of these individually. So I get the log of this constant. 20 times the log of 10 to the minus 4, that should be minus 80. Okay, so I got this guy here, minus 80. Comes along the bottom. Okay? All right, so I got that constant. Now, let's do this pole. So poles we know are flat at 0 and then drop 20 dB per decade. So in this case, that pole happens at 10 to the 5th. So this guy is nice and constant all the way along, nice and constant until I get to 10 to the 5th, and then he starts to drop 20 dB every decade. Okay, so I have the constant and now the pole. Now what about this character here, 20 log of omega? Well, this guy is basically 20x, right? So this is just a straight line. So let's show him cutting up through here. Like so. Okay, now this is the 0. This is the constant. This is the pole. What I have to do is add their effects up. Okay, I have to add their effects up. So that means that every given frequency, beginning over here, I need to say it is the sum of the pole plus the constant plus the 0. All right, I do that at every frequency. Easiest thing for me to do probably is to say, well, right here, right, the 0 is contributing 0. The pole is contributing 0. And the constant is contributing minus 180. Okay? So what that says is the sum of everything at that particular point is minus 180. The simplest thing for me to do is to say, well, at this point, the only thing that's active is the constant and this guy. So I just used the term there. I said active. The way I think about this is that, so at any given frequency, what's active, right? I've got a 0 that's active, causing me to change. I've got a constant, but the pole, right? The pole is contributing 0. The pole doesn't really become active and start contributing until I get above 10 to the 5th, okay? So at this point, basically what I say is, here, I can show the overall system is basically rising, okay, 10 dB or 20 dB every decade. So it's minus 80 here. It should be minus 60 here. It should be minus 40 here. It should be minus 20 here. It should be 0 here, okay? And then it should be 10 here, okay? So let's see. So I go from minus 80 here, minus 60, minus 40, minus 20, 0, 20, okay? So I know I got to get to 20. So, all right. Now, at that particular point, okay, at this particular point, I now begin to hit the impact of the pole. So at this point, I have a 0 that is causing me to rise 20 dB per decade, and I have a pole that is causing me to fall at 20 dB per decade, which means that overall, I am going to remain constant, right? Effectively, what I'm seeing is a 0 pushing me up, a pole pushing me down. If one is pushing at a constant rate upward and the other is pushing at the same constant rate downward, the total effect is that I'm just staying flat. All right, so this is our combined effect. Now let's look at that from MATLAB. I can see, right? So at 10 to the third, I'm at minus 20. 10 to the fourth, I'm at 0. 10 to the fifth, I'm at 20. Right, so the black line is my straight approximation. And then the blue line there is the actual value. So it's very, very close to each other. Now, if I look at the angle here, go back to the transfer function, right? So in this particular case, let's look at what our angle should do, right? So angle-wise, angle of h of s, in this case, so 10 to the minus fourth is a constant. I'm going to forget him. He gives me 0. Now, I said if I had a 0 at the origin, that's just a j omega term. So that means he gives me a constant 90 degrees. All right, and my pole, right, gives me that arctan function, omega over 10 to the fifth, like that. All right, so again, if I try to sketch that, so x equals log 10 of omega, and this is the angle of h of s, okay? If I try to sketch this guy, I have a 90-degree term that's basically stuck there all the time. All right, and then I have a 0 that begins to act at 10 to the fifth. So let's see, here's 1, so let's do 0, 1, 2, 3, 4, 5, 6, 7, right? So those are our linear points. And I call this, so log of 1 is 0, log of 10 is 1, 100 is 2, 1,000 is 3, 10,000 is 4, 100,000 is 5, 1,000,000 is 6, 10 million is 7, okay? So, all right, so for a pole, I begin to fall about a decade before that. So let's do, here's minus 45 degrees. A pole is going to have its phase go to negative 90. Okay, so 10 to the fifth, I should be equal to minus 45. Right, I start falling here, and I stop falling about a decade after. Okay, so in other words, at 1,000,000, that's a decade after the pole, I'm done falling. So I start falling a decade before at 10,000, done falling a decade after. Right on there, right on the pole frequency, I'm at negative 45 degrees. So at all frequencies, I add these up. So like right here, right, I have 90 plus 0. 90 plus 0, 90 plus 0. Once I get to here, I have 90 minus 45 is 45. By the time I get here, I have 90 minus 90 is 0. So that says the overall phase looks like this. All right, so I begin falling around 10,000, done falling around 1,000,000. So we go back, look at what MATLAB has. Okay, so there's our approximation. Looks like we're at about 90. Then we start falling. We're at 45 degrees, just like we predicted at 10 to the fifth. And then by the time we get to here, all right, we're at 10 to the sixth. So again, you see the straight line approximation and the actual really, really close to each other. All right, so that was a good set of examples. And now we have another set of stuff that we need to look at, which is how we look at second order systems.